Have you ever flipped a light switch and just stopped to think about what actually happens next? It feels so simple, right? But behind that one little switch is one of the most complex machines we've ever built. So today, we're going to dive into a surprisingly elegant solution to a really complex problem that, well, keeps our whole world running. So what you're looking at here is a super simplified picture of a power grid. In reality, it's this sprawling, continent-spanning network of generators, transformers, and power lines. Trying to manage this thing, making sure power gets from where it's made to where we need it, all without causing a blackout, is a massive challenge. It takes some incredibly sophisticated computer programs just to keep it all running safely and efficiently. And at the heart of that management is a tool called power flow analysis. You can think of it as the master calculator for the entire grid. It's the core program engineers use to figure out all the voltages and power flows across the whole system. It's absolutely essential whether you're planning for the future or just operating the grid day to day. But here's the catch. For decades, a really critical part of teaching this analysis has been a huge headache for engineering students. It was a real barrier to them understanding how to actually work with this vital system. And hey, don't just take my word for it. The authors of the paper we're looking at today describe the old method in some pretty blunt terms. Cumbersome, inelegant, and a total pain to program. This wasn't just, a minor inconvenience. It was a genuine roadblock for learning. And this right here shows you exactly why. Just look at this wall of math. This is what students traditionally had to deal with. They had to manually code all these complicated trigonometric equations just to build one of the essential pieces of their analysis. You can just imagine how frustrating and time-consuming that would be. All that math was used to build something called the Jacobian matrix. Now, this slide gives us a perfect analogy for it. See, the power flow problem is nonlinear, which means you can't just solve it in one straight shot. You have to take little iterative steps to get to the answer. The Jacobian matrix is like a GPS for the computer. It tells it which direction to step to get closer to the right answer with every single guess. It's absolutely crucial. But what if there was a better way? What if you could get that same crucial GPS guidance without getting totally lost in a forest of trigonometry? Well, that brings us to the hero of our story, an elegant new formula. Forget cumbersome and laborious. The new approach can be described with three simple words: concise, elegant, and simple. So, what does that elegance actually look like when you put it to work? This is it. You remember that whole wall of equations from before? All that complexity? It's now captured in these 6 clean lines of MATLAB code. And it does the exact same job as all those equations, but with just stunning efficiency. Now that is the power of a better formulation. I mean, the difference is just night and day. On one hand, you have the old way, wrestling with complex trig, a real barrier for students. On the other hand, the new way uses clean matrix code that's so much more accessible. It lets students get to the interesting part of the problem way, way faster. Okay, so here's the really crucial point, the real kicker. The breakthrough here wasn't actually inventing this 6-line formula from scratch. No, the true innovation was figuring out a brand new way to teach it. You see, this awesome, concise formula wasn't some big secret. It was already out there in high-level research papers. The problem was that the mathematical proof, the deep explanation for why it works, was based on stuff like higher dimensional derivatives, concepts way beyond a standard engineering curriculum. It was basically locked away in a language that students couldn't understand. So what the authors of this paper did was, honestly, it was genius. They knew a better tool was out there. They knew the key to it was locked behind all this advanced math. So what did they do? They forged a new key. They created a brand new proof using only the standard vector calculus that students already knew. They built a bridge so undergraduates could finally get their hands on this much more powerful and elegant solution. And this isn't just some clever idea on paper. This new, more accessible way of teaching has been the standard in the author's classroom for over a decade. It's been proven in the real world. And in that time, about 130 students have learned power flow analysis using this method. It's let them tackle much more complex networks far earlier in their education than was ever possible before. So why does a small change in a university classroom actually matter to the rest of us? Well, because it leads to smarter students, and smarter students lead to better, more reliable power grids for everyone. Let's just break it down. By making the foundational programming way easier, students can move on to the bigger, more complex problems much sooner. It frees up all this valuable class time that used to be spent just getting bogged down in tedious math.
And the bottom line is, the next generation of power engineers is walking into the workforce better equipped with more powerful and intuitive tools from day one.
And that really leaves us with a fascinating final thought. This whole story wasn't about a brand new discovery, but about finding a way to unlock something we already had. It just makes you wonder, how many other breakthroughs are out there, not waiting to be found, but simply waiting for a better teacher to show us the way?